Hello YouTube, my name is Abdallah Kiswani and today I'm going to be giving you an introduction to thermodynamics. So to start, I'm going to break down the word of thermodynamics into two words, which is therm and dynamics. What therm means is heat, and in thermodynamics we represent heat by the letter uppercase Q. The second half of the word is dynamics, or in Latin it's dynamis, is at the end, and that means force or strength or power. And we represent it by the letter W, which is work. Now both heat and strength or power is measured in joules because they are energies. Now, in thermodynamics, we have two main cycles that they teach you in thermodynamics. The first one is a power cycle. And what happens in a power cycle, we convert heat into work, such as mechanical work or any other work that we are familiar with. And it's also true that the rate of heat can be converted to a rate of work, and that's where the Q dot comes in, and that's, if I'm not mistaken, it's a Newtonian derivative, yes. The second cycle is a refrigeration or a heat pump cycle. Yes, question.
The dot, so you said Newtonian derivative, is that with respect to time?
It's dq dt.
Right, that's still invented by Newton, right? Is that what we were saying last time? With the dot?
Yes.
Okay, cool.
Yeah.
Very cool.
So it's the same thing, dw over dt. It's with respect to time. So the second cycle, what it does, it converts mechanical work or work into heat. And the difference between the two, a power cycle is considered to be a low-grade energy because a 100 conversion between heat and work is not possible. But to convert mechanical work to heat, you can actually have a 100% conversion or close to 100% conversion.
That's because of entropy, right?
Yes, that is because of entropy. So, since we have the cycles figured out, next thing would be the process. Like I have one state with a pressure, volume, and a temperature. I want to change that to have, for example, a different pressure, a different temperature. So a simple example of that would be a piston cylinder. So I have this cylinder moving up and down, and when it changes, we change the displacement of the piston, we get a change in volume, change in pressure, and change in temperature. So that's what's called a process, going from one state to another. And the main way we represent processes in thermodynamics is using a pressure-volume curve, or a pressure with specific volume. That's what we like to use in thermodynamics.
But what you're saying is that it only matters about the initial point and the final point, so it's conservative.
Between the two states, yes. Right. Mm-hmm. Yeah, and I'll talk about the conservation later. So, we have three main processes in thermodynamics, and they are isobaric, isochoric, and isothermal processes. And isothermal, I believe it's going to be familiar with you guys. Thermal is temperature, and we have, when it's iso, it's the same. So it would be, temperature would be constant. Isochoric, volume is constant, and isobaric, pressure is constant between the two processes.
But what that means is that, so if you're keeping the pressure constant, that means what you're having to do is change the volume and the temperature. And then same for the other ones, correct?
Yes, and we can actually represent that using what we know from chemistry, the ideal gas law.
Yeah.
Which is
setting a parameter constant.
Correct.
And then manipulating another two to
yes.
Is the power didn't go out, right? Remember that?
Yeah. Oh, this is beautiful, yeah. All right, so we have
$5.
So the ideal gas law, it's PV equal nRT. And if you give this to a thermodynamics professor, he would basically laugh at you, because in engineering we don't use the N. It's represented in kilomoles. That has no application in engineering.
They just raise the N?
No, we replace we replace the N. So if we want to use this equation, we have to put a bar because we represent the constant R with respect to kilomoles. But what we use is the PV equal the mRT, where we represent the amount in kilomoles to be represented in kilograms.
You guys don't use N times the big N times the Boltzmann constant times T?
No, we don't do that.
Oh, okay.
Yeah, that's physics people.
No, it's not that.
Yeah.
That's not what I'm referring.
So that's the equation we actually use, and we can rewrite this equation as well to be P specific volume RT. That's another representation of the same equation. So when we have an isobaric process where pressure is constant, that's the pressure right here, we can divide it over and we can get that V over T is going to be a constant for the isochoric. And for that's for isobaric. Isochoric would be V is a constant, so we divide it over and we have a P over T to be a constant, and isothermal would be PV equal a constant, and that's what Kyle was talking about.
So quick question. So the N is still the moles, right? And then the N,
Yes.
you're converting the moles to the mass.
It's basically, yeah, the
So
amount
you're
or the
multiplying by
mass.
Avogadro's number.
Yes, we are. Yes, yeah, and the R right here is what's
Rydberg
I was
constant.
thinking of
Yes.
avocado when.
Yeah, Avogadro, not avocado.
Hey, what's up?
so since we have these figured out, the
This is seating.
V over T is a constant, P over T is a constant, and PV is a constant. We can actually represent it here in our PV diagram, where if we go from state 2 to 3, we have a straight line going down, and we have our volume not changing. So this is an isochoric, as well as going from process state 4 to state 1 is an isochoric process as well. An isobaric would be this straight line down here, since our pressure is not changing. And what gets interesting is going from state 1 to 2, it's the PV equal a constant. And for the math people out there, these are two variables, so we can say that x, y is equal to a constant, and that's an equation of, you guys know?
No.
It's a hyperbola.
Isn't that a rectangular hyperbola? Isn't that the fancy name for it?
It's this dude right here.
Right.
Yeah, so that's
the
rectangular.
hyperbola.
Okay.
Yeah, wow, I didn't even, wow.
Yeah.
I'm surprised that came up.
I was
I read that on Wikipedia. Well, in college algebra, they teach you it's y equals 1 over x.
Yes.
So I'm like, this has to have a name, right? So I Googled it one day. And
Oh,
So
in
it's
this
the-
case, it's C over. Okay.
yeah.
So that's where this has come from, and that's the isothermal process
That
where
was
we
a
have a
question.
hyperbola.
Multiplying on both sides. That was a trick question. Quick question. So when I'm still stuck on the PV because when you change it to the mass,
Yes.
the units for the Rydberg constant have to change as well because
Yes. Yeah, this
So isn't that
this
gonna
whole value will actually change,
Change?
and there is a specific value for each substance you're trying to evaluate.
Oh.
Yeah, so there's a different R for water, ammonia, carbon, oxygen, and all that good stuff. Yeah, there's in thermodynamics, it's basically we have over like 50 pages of just tables over tables, and
In
that's
engineering.
in engineering. Yeah, yeah. You guys use one equation to derive everything. Yeah, we use
Okay,
tables.
Yeah, that's interesting. Okay.
Yeah.
So that's why it's not a factor when you're just writing in terms of variables because you know that the units will change and you'll be fine.
Yes, and the value will change depending
Yeah.
on the substance. So, we covered the cycle, the process, PV curve. Let's move on to systems. So,
Would this be like a 4,000 level class or a 3,000 level?
this is a 3,000 level class.
So sorry, one more comment, but the
Yeah.
importance of this, correct me if I'm wrong, but the importance of this is that you're seeing the different behaviors of gases in different states, which not only applies to engines and car engine stuff, but applies to stars and the universe itself. Like we use this kind of thing, at least in physics, we use this kind of the isobaric processes and the adiabatic processes, which he might get to another time, to apply to the universe itself.
So you use this in physics all the
This is
time.
deep stuff, like even in physics as well, but the same engineering mathematics, same as our mathematics and physics,
Yeah.
but like they use it to apply to engines. It's that same stuff that applies to the universe itself and stars
Interesting.
and stuff like that. So
Wow.
obviously stars a little bit more complicated because you have quantum mechanics, but
Hardcore.
Yeah, so that was an interesting comment
Deep
that you
stuff,
guys
really.
you use it for. It has different applications.
yes.
So, moving on to systems and thermodynamics, we have what's called an open system and a closed system. And a simple example of that would be if we have a beaker and it has water in it, and we put it on an oven or a stove where we can actually add our Q's, the heat. This will have a change in temperature, but the volume of our system, that's what we're analyzing, will stay controlled or constant. So when we have the lead open, or we don't have a lead, that will be considered an open system where we can have an interaction, energy and mass can interact with our system. Like we can have masses going out of our system, masses going back into our system. And when we
Interacting with the environment.
it's interacting with the environment, that's correct. And when we add a lid on top of our system, energy can still interact with our system. That's what we have the heat for. But the identity of mass will remain the same in our system. Mass cannot escape, it can only interact with itself in our system. And we have a special case of closed system. It's called an latent, system. And in isolated system, it has no applications in engineering because we have controlled volume, controlled mass, controlled energy, no change in pressure, no change in temperature. So it's basically just a glass of water sitting on top of a table doing nothing. So that has no application in engineering. I'm not sure if it has.
Well, it's impossible to have a purely isolated system because you're always going to have some kind of interaction with the environment. You can have a purely isolated system. Is that what you're saying?
I'm not sure about purely isolated system.
Purely isolated means it's completely isolated from the environment.
Yes, so it cannot interact with anything.
You can't have that.
Yeah.
You can't have a perfect one, right? That's
Yes.
what you're saying. Right.
Yes.
I know, obviously in physics, nothing, right? Because you put something in a vacuum of space, it's still going to have some kind of interaction because of the pressure, right? The molecules are going to
That is true.
the vacuum itself, right?
Yes.
Interesting.
All right. So we covered our systems and thermodynamics. Next thing would be is to actually have a numerical value representing changes in the processes, and that's where we have the work transfer. And the main work transfer we have in thermodynamics is called displacement work, and that could be going back to my piston cylinder. If I have a cylinder right here and it's moving a delta x distance, it will correlate to an area of a change in area. So if you want to derive the work, we go back to our specific definition in physics where work is force times the displacement. And I also have the definition of pressure, which is force divided by the area. And that's where pressure measured in pascals, you can convert it to newtons per meter squared. That's where the equation comes from. So if we solve for force right here, P A, if we substitute the force into our work equation, we get work equals to pressure times the area change in x or displacement. And area times the displacement, or if we work out the units, this is in meters squared, this is in meters, so we get meters cubed volume.
Is it really volume?
Yes, it is. Yeah.
Distance, right?
So we have work equals change in volume, and since we are engineers and math people, we like to take the integrals. So we can have a change in work and change in volume. Take the integral. I'm just going to skip a few steps and I can explain it. We can have the work from state 1 to 2. And if we actually do the integral from here, 1 to 2,
I see, got it.
we get W2 to 1, and that is equal to W1 to 2. So I just skipped a
That
step right
notation
here.
just means like W2 minus W1, is that what?
This is work going from state 1 to 2.
Okay.
That's the
Got
process. The
Think of, like,
process.
position 1, the work at position 1 will work to position 2.
So there would be like some type of like limits of integration here.
Yeah.
So
Yeah, going back to the example of the
It's conservative though, so you don't have to
Oh.
care about the initial point and final point.
yes. So that's 1. That's 2. I'll get to that. Yeah.
It's not a pure line integral. Like, you can prove that it's conservative such that you don't have to take into account the path of line integral. And what you
Right.
end up doing is you just Stokes theorem. You can go from the line integral to the area integral, the surface integral.
Yes.
But anyways,
So now we have work as the integral of P dV. And going back to our PV diagram, that work is the area under this curve.
Cool.
Yeah. So that's the numerical value of change in work.
interesting.
Yeah.
the volume at the 2 points.
Between the 2 points, yes. So, area under the curve. Now, to my last topic of this video is the first law of thermodynamics.
You learned this at the beginning of a course, like at the beginning of the thermal course?
This would be like the second day.
Second day?
Yeah. Second, third day. Yeah. So the definition of the first law of thermodynamics is the conservation of energy. And energy cannot be created or destroyed. It can only be transferred. So for a cycle, we have to take the sum of the work of that cycle, and it has to equal to the sum of the heat in that cycle. That's for the cycles. And for our processes, the definition is heat minus work is equal to the change in energy. And we can actually simplify it. If I want to do a classical mechanics example, if I take a ball and want to throw it up in the air, it will reach a point where the velocity would be equal to 0. So this will be a full kinetic energy, and this will be full potential energy. And what physics 1 classes teach you is to ignore air resistance. And that's, going back, is abusive. So if the ball is somewhere in the middle, it's actually interacting with air molecules and it's pushing it out of the way. So we have a loss of energy through sound, heat, and friction with air. Yeah. So what we can say is energy is equal to kinetic energy plus potential energy plus a change. Physics people like to put heat in here. But you can actually do internal energy, and that will account for rest of the changes in our system. So when we actually analyze thermodynamics problem, we can come into a conclusion that kinetic energy and potential energy are approaching 0. So we can take it out of the equation, and first law of thermodynamics would be Q minus W equal to the change in internal energy only.
You lost me. Am I the only one who's lost with that?
What were you lost about?
The kinetic energy equals potential energy.
It's not equal to the potential energy. Kinetic and potential energy are approaching 0.
Can we, why?
Well, you're analyzing like motion of air. And
Okay.
just like in physics where you ignore air resistance, we can ignore the motion of actual things that are moving and just analyze our internal energy of the system.
Oh, the net energy, okay.
Yes. Yeah, so kinetic and potential energy are approaching 0, and we only worry about the internal energy of our
Gotcha.
system. Got it? Okay. And that will conclude our video
Excellent.
and
Excellent.
on thermodynamics.
Thank you. Good
Yes,
stuff. Good
thank you,
stuff.
thank you.